Good morning, everyone.
Morning, sir.
So let's start. Okay. So in the last 2 to 3 classes, we had a discussion, a detailed discussion about what is a fuel cell, how to compare that with conventional energy generation systems. So what are the components? What is the working principle? What are the reactions? And is it enough to use just one single fuel cell, or do we end up connecting multiple fuel cells, which is known as stacking? And we also discussed about the historical developments of the fuel cells. And with all that, we learnt four new terms which are used in common to compare between the fuel cells as well as between fuel cells and conventional energy generation systems. So, which are those terms? So, one is the current density. So, current per unit area. So, if nothing is specified, unit area will be the area of the electrode. There are possibilities where they speak about the area of the electrolyte as well. So in that case, it will be specifically mentioned. If nothing is mentioned, current density is always current per unit area of the electrode. And what are the units? So milliampere per centimeter square or ampere per feet square. And usually when current density is mentioned or expressed, the associated voltage should also be mentioned. And in general, on an average, this voltage will be between zero point 0.6 and zero point 0.7. So that purely depends on the type of fuel cell. In some cases, it may go up to 0.85 and zero point 0.9 as well. So next such terminology is power per unit area. So when it comes to power, there are three terms. So one with respect to mass, another with respect to volume, another with respect to area. So kindly keep your microphone on mute. Abhirup?
Hello, sorry, sir.
Yeah, no problem. Okay, thank you. So power per unit area, power per unit mass, that is specific power, watt per kilogram, power density, power per unit volume, so milliwatt per meter cube. So don't get confused between current density and power density. Current density is always with respect to area, and power density is always with respect to volume, unit area and unit volume respectively. So keep that in mind. So on top of that, it is the price per kilowatt, volume per kilowatt, and life cycle of the fuel cell. These are three terms that are used to speak about price of a fuel cell. Okay. So with that, there are few general advantages of fuel cells. So one is the efficiency. Fuel cell systems are more efficient than IC engines. They are usually compact, and in some fuel cells we have the advantage of CHP as well. CHP is combined heat and power. So along with the power that is generated with the fuel cell, there is some waste heat generated because of the reactions that are taking place. So that waste heat is recovered, and that heat in turn is used to generate additional power. So such systems are known as combined heat and power systems. So simplicity, that is what a fuel cell is also known for. And components, there are no moving parts, so highly reliable systems, and comparatively long lasting. So reliability comes into picture for premium applications. So applications such as hospitals, banks, the uninterrupted power supply is very important. So in such cases, fuel cells are very reliable. Coming to the emissions, a conventional hydrogen oxygen fuel cell generates just water along with electricity. So, but considering other fuel cells, there might be some emissions depending upon the type of fuel that is used. So there might be some emissions. In spite of that, fuel cells have very low carbon footprints. So the oxides of carbon generated are very low. And very quiet systems. There is no noise generated out of working of fuel cell. These are some of the general advantages of fuel cells and fuel cell systems. So here you can see how compact an engine of a car is when a fuel cell is used. So this is an example of engine, internal combustion engine that is used in Benz A-class car, and the capacity is around 75 kilowatt. So, look at the module. So PEMFC is used. So polymer electrolyte membrane fuel cell module is used. Consists of multiple fuel cells stacked together. Look at the size and volume. It's very compact. And the picture on the right speaks about different types of fuel cells that can be used depending upon the power requirement. Say if you consider DMFC, that is direct methanol fuel cell, so it ranges from 1 watt. It can be as small as 1 watt and it can go up to 100 watts. Alkaline fuel cell, so it is in the order of 1 to 10,000 watts. Then if you consider molten carbonate fuel cell, so it's in the order of megawatts, so 1 megawatt to 10 megawatts. Usually such systems are for electricity generation on large scale, which can be compared with conventional hydroelectric power generation. And SOFC and PMFC have comparatively wide range of application. So if you consider PMFCs, that is polymer electrolyte membrane fuel cells, it can be as small as 1 watt and it can go up to 100 kilowatts as well. And likewise, SOFC, it can be from 1 kilowatt to 10 megawatt. And PAFC, it is from around 10,000 watts to 1 megawatt. So this is on an average application based on the power requirement. Okay, so now let's try to learn some thermodynamics associated with the reactions that take place inside the fuel cell. Okay, so what is the definition of a fuel cell? It is an electrochemical device or energy conversion device which converts the chemical energy of fuel and oxidant directly to electricity. So now we need to know what is this chemical energy? What is the chemical energy we are talking about? And when it comes to electricity, so we also need to know few other fundamental terms. So power, which is product of voltage and current, and energy, it is product of power and time. So now the very basic understanding of current and voltage. So in layman's terms, the current can be compared with the flowing water or kinetic energy of water. Voltage can be compared with the potential energy of water or the pressure. And coming to the chemical energy, so it is also known as the chemical potential. So this chemical potential consists of three terms. Okay, so Gibbs free energy, enthalpy, and entropy. And let's look into each of these terms. So enthalpy is the total heat content or energy content of any chemical substance. And when it comes to utilization of such enthalpy, we cannot completely make use of it. So that enthalpy consists of two forms. One is usable form, another one is non-usable form, meaning if you try to extract the energy from a chemical substance, you cannot completely utilize all the energy that is present in that substance. So some energy will always be lost. So the non-usable part of energy is entropy. The usable part is Gibbs free energy. So what are we talking about? We are talking about chemical energy or chemical potential of a substance. So which can be compared with or defined as enthalpy, the energy content of a system, and it consists of two parts: usable part, non-usable part. The non-usable part is entropy, usable part is Gibbs free energy. So energy available to do external work, and here any work that is carried out because of change in pressure or volume is neglected. So that is how the Gibbs free energy is defined. So now we have elements and compounds, and coming to the Gibbs free energy, so there is another term known as Gibbs free energy of formation. So this Gibbs free energy of formation for an element is zero. Okay, and the Gibbs free energy of formation exists only for compounds. So if we take the overall reaction of a conventional hydrogen oxygen fuel cell, so this is the overall reaction when a conventional hydrogen oxygen fuel cell is considered. So in such a conventional fuel cell, what is the reaction that is taking place at anode? So the hydrogen fuel gets oxidized, gets split into protons and electrons. That is the reaction that happens on anode. At anode, move through the external circuit and reach cathode. These protons, electrons combine with oxygen, so forming oxygen and water is formed. So this is the overall reaction. In such a reaction, we have both elements as well as compound. So which are the elements? So the reactants, hydrogen and oxygen, are elements which has no Gibbs free energy of formation. And when it comes to water, which is a compound, there is Gibbs free energy of formation for that. And it is always the change in Gibbs free energy of formation, that is delta GF. Okay, so G, capital G, is the representation for Gibbs free energy, and subscript F indicates that it is Gibbs free energy of formation. So this delta is change in Gibbs free energy of formation, and small g with an over bar indicates that it is the Gibbs free energy of formation per mole of substance. Okay, so usually we speak about in terms of moles, and if you want to find out the change in Gibbs free energy of formation per mole of water or per mole of this reaction, So it is usually the Gibbs free energy of formation of products, difference of Gibbs free energy of formation of products and Gibbs free energy of formation of reactants. If we take that difference, we get change in Gibbs free energy of formation per mole. So we just now realized that the Gibbs free energy of formation for elements is zero. So this part will be zero. So essentially it is the Gibbs free energy of the water, which can be utilized in case of a fuel cell. Hello. So we are just trying to understand the thermodynamics behind the working of a fuel cell. So in a conventional fuel cell, we supply fuel, that is hydrogen at anode, and oxidant oxygen at cathode. So reactions take place at both the electrodes. And if we consider the overall reaction, it is the combination of hydrogen and oxygen forming water plus electricity. So if we want to find out the usable part of this reaction, usable energy, usable part of energy of this reaction, so we have to take Gibbs free energy of formation into account. And it is the change in Gibbs free energy of formation that can be utilized or that can be effectively converted into electricity. So how do we calculate that? We have to take the difference of Gibbs free energy of formation of products and reactants. So in this very particular reaction, what are the reactants? So hydrogen and oxygen. What is the product? Water. So there is Gibbs free energy of formation for.
So your voice is breaking.
And this Gibbs free energy of formation of water depends on the temperature. Hello. So can you hear me now?
Yes.
Okay.
Yes.
So just now I realized that the network connectivity is lost because in the when I am doing the slideshow, I'm not able to make out anything about the network or about the Google Meet. So I just connected using my mobile phone now. So I have connected from college today, and then there seems to be some network issue. So what is the last thing that you heard? Hello.
Sir, gives
So the
frequency.
reactants part gives energy.
Okay. Get free energy. Just a minute. Let me try to. You are not able to see the slide now, right?
No, sir.
No, sir.
Yeah. Okay. Okay. So have I already shared this presentation with you on Google Classroom? Hello.
No, sir.
No.
I think Unit 1 notes is there, sir.
Uh, I I am not sure whether it is reference material or presentation. Can anyone just have a look? In the meantime, I'll try to open the presentation on phone.
It's not there, sir.
Sir, it's
It's not
reference.
there. Okay. Yeah. That's what even I remember. Just a minute. So are you able to see the presentation now?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Just a minute. Okay. So it's visible, right? Did you get to listen to
Yes, sir.
this? Did you get to listen to the explanation of all these terms on this slide?
Not everything, sir.
Okay. So this part was clear, right?
Yes, sir.
Yes, sir.
Okay. Okay. So now let me just repeat. So we are just trying to find out how much energy can be effectively converted into electricity in a fuel cell. So what is that? Going to the definition of the fuel cell. So it is the energy conversion device which converts chemical energy of fuel and oxidant effectively or directly into electricity. So now we need to know how much part of this chemical energy is converted. So for that, we understood the definition of the chemical potential. So it consists of two parts, that is usable part, non-usable part. So that non-usable part is entropy and usable part is Gibbs free energy. So coming to Gibbs free energy, we actually consider the Gibbs free energy of formation, and this Gibbs free energy of formation for the elements is 0, and it exists only for the compounds. And looking at the reaction on the screen, so this is the overall reaction that takes place in a fuel cell. So what is happening? We are supplying hydrogen at anode and oxygen at cathode. So what is the reaction that takes place at anode? It is the hydrogen that gets split into protons and electrons. Protons move through the electrolyte. Electrons move through the external circuit. And at cathode, the electrons that come from the external circuit and the protons that come through the electrolyte combine together with oxygen, forming water. That is the reaction at cathode. So if we take the overall reaction, so it is this: the hydrogen fuel combines with oxygen oxidant, forming water and electricity. So in this reaction, so hydrogen and oxygen are reactants, water is the product. And when we try to find out the Gibbs free energy of formation, it is actually the change in Gibbs free energy of formation is what we can effectively utilize. So how to calculate the change in Gibbs free energy of formation? It is Gibbs free energy of formation of products, difference between products and reactants. And the G is the representation for Gibbs free energy. F subscript represents the Gibbs free energy of formation. This delta represents change. When we consider small g with an overbar, it is the Gibbs free energy of formation per mole of substance. Okay, so like that, we are interested in change in Gibbs free energy of formation. When overall reaction is considered, the product is water and the reactants are hydrogen and oxygen. The GF Gibbs free energy of formation for reactants is 0. So ultimately in this reaction, it is only the Gibbs free energy of formation per mole of water is what we can make use of. And this is dependent on temperature. With increase in temperature, the change in Gibbs free energy of formation of water decreases. So looking at this, the negative sign speaks about release of energy. So it is the number that matters. So the number, the value decreases with increasing temperature. What is the meaning of this? If we carry out this reaction at room temperature, the change in Gibbs free energy of formation that can be effectively utilized to generate electricity is more. Okay, that is what we can understand from this table and the reaction. So any questions in this regard? Is this clear? I hope I am connected now and you are able to hear.
Yes, sir.
Okay. So if no questions, I'll just proceed further. Okay, so now let us assume that this delta GF is completely converted to electrical energy. And this is an ideal situation, and it is known as under no loss conditions. So in such a case, for every molecule of hydrogen, every molecule of fuel that is consumed, in particular hydrogen is consumed, 2 electrons are generated, and these 2 electrons pass through the external circuit. So when 1 mole of hydrogen is considered, so it consists of Avogadro number of molecules in it. So that is 6.023 into 10 power 23. That is the count, number of molecules in 1 mole of hydrogen gas. So how many electrons do we get because of that? It is 2 times the Avogadro number. 2n electrons pass through external circuit when a mole of hydrogen is consumed. And to express the same thing in terms of charge, so electron has a charge, so that is minus E, and you multiply that with this 2n, and that is the quantity, the amount of charge that is generated for every mole of hydrogen that is consumed, which is expressed in terms of coulombs. This Ne, the product of Avogadro number and charge on electron, is collectively addressed here as F, that is Faraday's constant, which is 96485 coulombs. So now we realized what is the charge that is generated when 1 mole of hydrogen fuel is burnt or consumed in a fuel cell. So if we proceed with that, we are trying to find out how much voltage is generated in a fuel cell. In order to find out the voltage, we consider the charge that is generated, that is electrical work done, so electrical work done per charge. This is not change, this is charge. Okay, so it is the ratio of electrical work done and charge that gives the voltage, and it is represented as E. So soon we are going to learn why it is E. So for now, how do we get that? It is the electrical work done by charge, that is delta GF by 2F. Okay, so that is how we can find out how much voltage is generated in a fuel cell. And why is it E? Because it is the electromotive force that is known as EMF or electromotive force or reversible open circuit voltage of a hydrogen fuel cell. So this is how we can find out how much voltage can be generated in a fuel cell. Now let's take an example. So in this example, the fuel is hydrogen and the fuel cell is being operated at a temperature of 200 degrees centigrade. So at this temperature, so the change in Gibbs free energy of formation per mole is 220 kilojoules, and using that, if we calculate the voltage, it will be around 1.14 volt. That means under no loss conditions. So when the circuit is open, the open circuit voltage that can be generated in a fuel cell where hydrogen is used as fuel and operated at 200 degrees centigrade, it is 1.14 volt. Right? Is this clear? Okay. If no more questions, let's proceed further. And this is an example of how you calculate the voltage generated in a fuel cell depending upon the type of fuel and the operating temperature. So if you want to generalize this reaction, so if you remember, what is this 2? This 2 are the number of electrons, okay, that are generated when 1 molecule of hydrogen is consumed. So that means if some other fuel is used, this number may vary. Okay, so it could be a different number than 2. So in that case, if you want to generalize this, E equals to negative of delta GF by NF or ZF. So that Z represents the number of electrons generated when each molecule of fuel is consumed. Okay, so that is what is shown here. So if you want to generalize this, the open circuit voltage or electromotive force or voltage of a fuel cell can be calculated using this equation. So here Z represents the number of electrons transferred or generated when each molecule of fuel is consumed. And F is Faraday's constant. So let's consider another example, a methanol fuel cell or DMF, or direct methanol fuel cell, where fuel is methanol. In such a case, the number of electrons generated are 6. And if you try to calculate the E in that case, so it will be 1.21 volt. And soon we are going to learn different voltages. The voltage now we are talking about is the reversible open circuit voltage or the electromotive force. So what is this open circuit voltage? That means, if you remember the components of a fuel cell, so load is an essential component of the fuel cell. After all, the load is the one which consumes the electricity that is generated in a fuel cell. When a fuel cell is not connected to such a load, so it is known as open circuit. The circuit is open. The circuit is not complete because the load is not connected. So if you measure the difference in potential between the two electrodes, so whatever the difference in potential you get is nothing but the open circuit voltage. Okay. Okay, that is about what is the chemical potential, how much of that chemical potential can be utilized, how does it depend on the temperature. That is what we discussed so far. So now let's learn a little more about the fuel. So far, whatever we have heard is only hydrogen. That means hydrogen is the essential fuel for fuel cell. But during the discussion, we also came across that any other fuel can be used. So it can be a natural gas or hydrocarbons. However, these fuels should be processed in order to get hydrogen. Ultimately, that is the hydrogen that makes this fuel cell run. In most of the cases, of course, there are exceptions. There are certain fuel cells where fuel other than hydrogen can also be used. In general, most of the fuel cells require hydrogen as fuel. If you do not use pure hydrogen as fuel, so you will start with other materials such as natural gas or hydrocarbons or many other substances. But at some point of time, you process that fuel and make sure that hydrogen is generated. So the gaseous stream that enters the fuel cell as fuel will mainly consist of hydrogen along with other gases. So now we are going to learn a little more about these fuels and fuel choice. So any chemical substance capable of undergoing chemical oxidation and any oxidant that can be reduced at anode and cathode respectively can be used in this fuel cell system. So that is in general. And fuel cells can use oil, natural gas, coal and methanol as fuels, and that depends on the type of fuel cell as well. And however, if it is a fuel other than hydrogen, so you should subject that into pre-processing so that we get hydrogen. Ultimately, it is the hydrogen-rich gaseous mixture that enters the fuel cell. And the hydrogen that is required can also be generated by splitting the water. Okay, by subjecting water to electrolysis, by electrolyzing the water, we can generate hydrogen. Such hydrogen can also be used in fuel cell. Actually, that is the purest form. So that is the ideal case, which is very good for a fuel cell. And the efficiency of a fuel cell is high or maximum when pure hydrogen and pure oxygen is used. And by subjecting the fuel other than hydrogen to pre-processing, so we extract the hydrogen. And few other examples are gaseous hydrocarbons such as natural gas and propane, light hydrocarbon liquids such as naphtha and methanol, and heavier hydrocarbons like fuel oil and coal. All these can be used as fuel in a fuel cell, but again, it is specific to type of fuel cell, and the pre-processing is specific to the starting material. Here are some other examples. So methanol can be used, ammonia can be used, hydrogen, methane. These are some of the other fuels. However, there are some disadvantages associated with all these fuels other than hydrogen. So coming to the hydrazine, if you consider the Emax or the maximum uh, voltage that can be obtained when hydrogen is used as fuel, it is 1.28, which is even more than hydrogen. But the disadvantage here is this hydrogen decomposes into very toxic chemicals, okay, which is not all suitable for usage in fuel cells. So ideally, theoretically, if you speak about the chemical substances that can be utilized as fuel, so hydrogen can definitely be used as fuel. Uh, but there are associated disadvantages of using hydrogen as well. So we are talking about the ideal or theoretical cases here. So likewise, ammonia can also be used. However, the voltage that can be generated is comparatively less. This is about the fuel choice. Okay. So essentially, these are the topics of Unit 1. And any doubts in this regard? So you kindly get clarified. So maybe by the end of the day, I will share this presentation as well on the Google Classroom. So kindly go through it. So what I suggest you is this presentation is prepared for my convenience. So just to convey the information to you, I always insist you guys to go with the reference material. Okay, so presentation is just an indication. Not all the information is available on the presentation. So kindly go through the reference material that is already posted. And when it comes to the tests and quizzes, so the questions may come from the reference material as well. It is definitely not only based on the information that is posted on the presentation PPT. Okay, that is for your information. So any questions in this regard?
No, sir.
Okay. So that's it for today, and we shall take the attendance. Okay. Today is 18. Wow, it is taking more time than expected. Just trying to open the spreadsheet and it's taking more time. Okay, and one more reminder regarding formation of teams. So kindly complete it before the deadline, that is 20th. So you can post your teams on the Google Classroom in the discussion forum, or you can just send me an email as well. But complete that task before 20th. Okay, so today is 1809. Okay, Pradeep Kumar from Aerospace.
Present, sir.
Okay,
Sir,
so
doubt, sir.
Nandini. Yeah, yes, Pradeep.
Sir, 4 is compulsory, sir.
See, the main objective is to come up with a review paper by the end of the semester. And in order to publish a review paper in a Scopus Index journal, the minimum number of articles that you should come up with are at least 200. So if it is 4 people, it is just 50 per person. If the number of people in the team goes down, then the burden on you will be more. So you will end up finding more papers. If you are comfortable with that, I have no issues. But I suggest that to be a minimum of 3 and a maximum of 4.
Yes, sir.
Sir, can we do a group of 5, sir?
5 again is a little work. So 4 is ideal. So the worst case scenario, if you are able to justify,
Sir, if we
then
do 5, like we can do some extra papers also. Like when 5 of us are together, like because if we are 5 friends, then like we would all prefer to be together, sir. Like
okay, yeah. Let us see. For now, let it be 4 in the worst case scenario. So let it be 5. But I suggest you to make it a team of 4. Anyways, you suggest, we shall see. But I cannot guarantee you. For now, it will be 4. But I will let you know once I get the entire list.
okay, sir.
Yeah. Fine. Nandini from Aerospace. Aditya Datta.
Yes, sir.
Okay. And Sharat.
Present, sir.
Prajwal. Prajwal Hiremat.
Present, sir.
And Shritij. Ravi Krishna. Yes, Pawan from Biotech.
Yes, sir. Present, sir.
Okay. Nisha.
Present, sir.
Okay. Spurti.
Yes, sir.
Okay. Riya Sharma.
Present, sir.
Abhipsa.
Present, sir.
Okay. Soumya.
Present, sir.
Shreya.
Present, sir.
Apurva.
Present, sir.
Amulya.
Present, sir.
Prasanna.
Yes,
Prasanna
sir.
Reddy.
Yes, sir. Yes, sir.
Okay. Harini Subramanian.
Present, sir. Present.
Preksha Shetty. Ambrish. Srinidhi Rachappa. Praveen Khanna.
Present, sir.
Aditya Anand. Pooja. N. Pooja from Computer Science.
Yes, sir.
Prerana KS. Divyanshu Anand.
Present, sir.
Geeta Shivani.
Present, sir.
Hrishika Rai.
Present, sir.
Himanshu.
Present, sir.
Anirudh Devpura.
Present, sir.
Ayush Srivastava from Computer Science. Sandesh Nayak. Mahant.
Present, sir. Excuse me. Sandesh, present, sir.
Sandesh. Okay. And Rajashekara.
Present,
Rajashekar.
sir. Present.
Yeah. Utkarsh Kumar.
Yes, sir.
Ajay B.
Present, sir.
Mahesh Basavaraj.
Present, sir.
Santosh Dodamani.
Present, sir.
Srinath. Srinath L.
Present, sir.
Mithun Nayak.
Present, sir.
Satyansh Singh.
Present, sir.
Saurabh Kittur. Sharan C. Tushar Goyal.
Present, sir.
Subhash VN.
Present, sir.
Channabasava. Gundappa.
Present, sir.
Okay, Channabasava is present. Gundappa. Kiran K.
Present, sir.
Salim. Rohan Akash.
Present, sir.
Sayam Agarwal.
Present, sir.
Nitya.
Present, sir.
Arpit Kapil.
Present, sir.
Suman Saurabh.
Present, sir.
Sheetal SP. Yashika Harish.
Present, sir. Present, sir.
Shahid.
Yes, sir.
Kushal R from electronics. John Bosco from electronics. Okay. Anuraj. Ujjwal.
Present, sir.
Arjit Banerjee. Shubham Bansal. Kushagra Kumar.
Present, sir.
Fatima Tabassum.
Present, sir.
Ishita Mudaliar.
Present, sir.
Zainab.
Present, sir.
Anirudh Sharma.
Present, sir.
Akash Tripathi.
Present, sir.
Nalin Kamal. Jayat.
Present, sir.
Girish Gowda. Pranav Pathak. Prajwal Panchangam. Yes, Ketan. Yes, Darshan.
Present, sir.
Mahadev R.
Yes, sir. Present, sir.
Kushal Gowda. Himanshu Sharma.
Yes, sir.
Ronak R.
Sir, present,
Sagar.
sir. Sir, Ronak, present, sir.
Okay. Sagar Biswari.
Present, sir. Sagar.
Yeah. Tushar Agarwal.
Present, sir.
Purvi Seth.
Present, sir.
Okay. Aditi.
Present, sir.
Riza.
Present, sir.
Abhirup.
Present, sir.
Ashutosh Agarwal.
Yes, sir.
Aditya
Ashutosh present,
VS.
sir.
Okay.
Yes, sir.
M. Rakshit.
Present, sir.
Okay. Rishabh, Bhargava, Bhavit Shetty,
Present, sir.
Anuj Kumar Nigam,
Present, sir.
Ashwin Sudarshan,
Yes, sir. Present.
Sadashiva Hebbal, Mallika Gowda,
Present, sir.
Sohangi Srivastava, Nabira Shivansh, Ayush Srivastava.
Present, sir.
Okay, Nabira.
Sir Shivansh.
Yeah. Ayush Srivastava from EC, if I am right. Siddharth Prasad from Civil.
Present, sir.
Okay.
Present, sir.
Yeah. So I got your name included in the list. So I got the recent list yesterday.
Yes, sir. Actually, like, can you just add me to the Google Classroom itself? I don't have like access to the materials and also.
Okay, fine.
Yeah.
So what
Thank
I
you, sir.
suggest you is just
Yes, sir.
send a message on WhatsApp, and
Yes, sir.
also you post your mail ID so
Yes,
that
sir.
it becomes easy for me to add you.
Yeah, okay, okay, sir. Yes, sir.
Yeah, fine.
Sure, sir. Thank you, sir.
Thank you all.
Sir?
Yeah.
Sir,
Excuse me, sir.
Yeah,
Sir, Nandini
Sally.
from Aerospace is present, sir. Her microphone is not working.
Okay, just a minute.
Sir, Praveen from Biotech present, sir.
Just a minute. First is Nandini. I hope she was present. Okay, and then who's next?
Praveen from Biotech, sir.
Okay, one by one. Praveen from
Biotech.
yes, Praveen. No,
Sir,
Praveen
Amrit.
Khanna. Praveen.
Sir,
Khanna,
Preksha
right?
from Biotech.
Just a minute. I'm just looking for Praveen Khanna. Praveen Khanna is marked present. Okay, next is Preksha. Preksha.
Sir, Preksha.
Just a minute. Preksha Shetty. What is your USN?
037.
Preksha is from
Biotech department, sir.
Biotech. Did I call your name
Biotech
before?
department.
Did I call your name before?
Sir, my mic wasn't working, so I logged in again.
No. I just want to make sure that your name is there listed. Yeah, okay. Yes, it is there. Preksha, yes.
Sir, you
Okay.
called me yesterday.
Yes.
Sir, Amulya Rao
marked.
from Biotech, sir.
Yes, Amulya. In attendance, right?
Yes, sir.
Yeah, I have marked it. Yeah.
Sir, Aerospace Department, Shretaj.
Shritij.
Sir, Amrish from Biotech is present, sir. His mic is not working.
Okay.
Amrish,
I hope so. Yes. Okay.
he was in the meeting, sir. Then again, he lives in village, so the network issue was.
Okay, fine. I have marked as present. Yeah. Next. Salim from Civil, right? Salim. Okay. Present. Yeah. Anyone else? Did I miss anybody? Okay. So if not, thank you.
Thank you, sir.
Shahid is marked present.